automated podcast.
Welcome to Automated. I'm your host, Mark Verbenkov, and in this weekly podcast, we will be exploring the impact of emerging technology on jobs, society, as well as us, with business and technology leaders, researchers, and independent professionals across the world. So today we'll be talking about bioprinting functional organs. So when I actually first heard about this technology some 7 to 8 years ago, it was through a TED Talk. I was pretty shocked that we actually had the capabilities to actually print an organ that can be used to transplant into a patient and have it actually work. Now the technology has drastically improved since then, and you'll hear about this in the conversation today, where an actual human heart can be printed. So Stephen Morris, founder and CEO of Biolife 4D, comes onto the podcast to talk about his company, how they are printing hearts for future organ transplants, what the social impacts of this are, as well as what the future vision is regarding this technology. So Stephen has more than 20 years of extensive experience in the precision machining and manufacturing industries, including 15 years serving as president of privately held Inland Midwest Corporation. So actually, after successfully selling the company, he formed a consulting company focused on achieving sustainable manufacturing solutions. But upon recognizing the nearly unlimited financial and human potential of bioprinting, he formed Biolife 4D, which is now an industry leader. I really enjoyed this conversation. I think that if you haven't heard about bioprinting before, this will be really interesting for you, as both the technology as well as the social impacts are pretty extensive. Well, thank you very much, Stephen, for coming on to the Automated podcast. It's great to have you here and talk a little bit about bioprinting, which I think is a very interesting subject.
Well, thank you for having me. I'm excited to tell you about what we're doing. It's pretty incredible technology, and I'm glad to share it.
Awesome. So one of the things that I always do with my guests to start off with is just a little bit more of a kind of a personal or a human approach. What made you initially interested in bioprinting, and as we'll be talking about 3D printing human hearts, which is really cool?
It's a great question. The answer is it was a total accident. So my last company was a medical device company, and after I sold that and stayed on for a few years, I left and decided I wanted to do something different, but I was under a non-compete, but I wanted to stay in the same industry. So I went back to my customers and I said, hey, listen, I'm going to open up a rapid prototyping house. Instead of taking 3 or 4 months to do a prototype of a surgical instrument or a medical implant or something like that, what if I can do it for you in 10 days? And they said, that's wonderful. And what I told them, I was going to open up a 3D rapid prototyping house. So I had a great relationship with my customers. They said, go ahead, do that, whatever capacity you have, we'll fill that capacity. So my goal was to start a 3D rapid prototyping house, and I knew a lot about it, but I wasn't an expert. So I really had to do a deep dive onto it. When I was doing that, literally just by accident, I kept coming across articles about 3D bioprinting for the medical space. And I would look at them and say, wow, this is incredible, but no, this is science fiction. There's no way this could be. And I kept by accident coming across more and more articles, and finally I said, you know what, I really want to look into this. And I did, and I went out and looked for who are the leading people doing research in all of the different areas that it would take in order to make this technology really commercializable, bring it out to the market. And I went and talked to them, and all of them said the same thing. We're finally at a point in human history where the computing technology and software technology and life science technologies are all at a point where we're at that precipice where we can come together and push this technology out to the market. So I asked these people, how come you've never done that? And they've all said, their funding is primarily through grants. And when you write up a grant, you have to kind of stay within the wheelhouse of that grant. So they never really had that opportunity to expand out. So I said, hey, listen, each of you kind of represent a piece of this puzzle, and we know where all these pieces go. What if we all came together, formed this company, and let's push this technology out to the market? And they all said, yeah, let's do it. So I went home to my wife and I said, hey, on one hand, we can start this rapid prototyping house, and I know financially it'd be great. Or I can start this company, Biolife 4D, and if we're successful, we literally could be saving millions of lives globally every single year. It's pretty incredible.
Mhm.
And what do you think? And she said, it's an easy answer. So that was the beginning of Biolife 4D.
Awesome.
Yeah.
That's a super interesting introduction. I also think that, I mean, for myself, when I first came across bioprinting, and I think from the conversations that I've had with people over the years, it's really something, as you said, it's like a little bit science fiction-y, right? It almost sounds like it's too good to be true, or the technology is just not there yet. But I think that this has been around for some years now. Yeah.
It has, yeah. So 3D printing's been around literally since the mid 80s, and
Hmm.
people don't realize that. But bioprinting has actually been around since around 2003. And that was the first time that someone started taking the 3D printer and applying it to biological applications, bioprinting. And really, 3D printing and 3D bioprinting are relatively similar. The 3D bioprinting is just a special subset of 3D printing, but it's designed to protect the cells. Most
Hmm.
normal 3D printing, you essentially melt one layer onto the next. You start at the bottom, you work your way up, or now these days the opposite way. But you're literally kind of melting one layer together, and that's how you form your construct. You couldn't do that with cells because
Right.
you kill all the cells. So it's a very specialized type of 3D printing, but it is a subset of 3D printing. It's
Hmm.
been around, and it has been around for almost 2 decades now.
Yeah, yeah, that's I actually just had a conversation with a friend the other day, and I was mentioning like, hey, I'm going to have this, very interesting discussion about bioprinting, and they were I think the proper term is flabbergasted that something like this existed. So I think it's really interesting to hear that it's been around for 2 decades already.
Yeah, that's this whole technology. That's the most common uh, feedback that we get
Yeah.
is wow, it's incredible. I get it, but it sounds too much like Star Trek or Star Wars, or depending on how old you are, how it sounds more like Buck Rogers. Some of the old
Right.
people. But it's really not science fiction. It's science fact. Where the
Yeah.
stuff that we're doing is just to me mind-boggling. It's just
Yeah.
incredible, and it's super exciting.
I want to go back to one of the first things that you said there about saving lives. I think it'd be good to give maybe a little bit of context regarding transplants and organ donations and things like that. And I was reading on the website that you had like stats for transplant rejections and how many people are dying. Maybe you can give a broad overview so that people can understand to kind of what extent people are dying or having complications without this technology being applicable right now.
Sure. So for particular stats, if people are interested, they can always go to our website,
Hmm.
biolife40.com. But let me give you some general ones, which were pretty much the driving force as to why we're doing what we're doing. One out of every three people in every developed country in the entire world die of cardiovascular disease. By far, it's
Yeah.
the leading cause of death. In the United States, it's more than every single type of cancer combined. And that's not uncommon. It's common for every single developed world. The reason I say developed world is because in countries where people don't live long enough to have heart disease, they may die of malaria or something like that. But people that survive a normal lifespan, the number one killer is heart disease or cardiovascular disease. And the incredible thing is, as you go to late stage heart failure, if you were to need a heart transplant, there's so few of them that are available. So when I was trying to decide what organ Biolife 4D was going to concentrate on, I chose the heart. And it was a little bit interesting to me because there's tens of thousands of people on kidney transplant waiting list and tens of thousands of people on heart on liver transplant waiting list, but there's only 3,500 people on the heart transplant list. And I'm like, well, wait a second. If one out of every three people die, that's way more than people that have kidney disease or liver disease.
Yeah.
Why
Yeah.
is that? And the reason is because there's such a lack of supply of donor organs, we literally have to ration those hearts that become available. The most amount of hearts we've ever been able to transplant in the United States in 1 year, believe it or not, is only about 3,500, which is why they keep the transplant waiting list to that. They literally
Hmm.
ration. So if you have diabetes, or other conditions, you may not even be eligible to get on the heart transplant waiting list. As a matter of fact, just in the United States right now, there's about 200,000 people that have late stage heart failure whose life could potentially be saved by if they were to have a donor heart transplant, but they're not even available. So they literally have no hope. So one of the main things that we're doing by bioengineering a heart is we're addressing that lack of supply. Even more incredible than only 3,500 transplants in the United States, donor heart transplants, is the rest of the world combined is only another 1,500 heart transplants. The
Really?
whole rest of the world, countries like Israel that are so technically advanced, they only have a couple of dozen that they do a year.
Hmm.
So it's a major problem. And if we're able to provide a solution to the supply challenge, we literally will be able to be saving millions of lives a year. Now, our technology, beyond saving people's lives, really takes it to the next step.
Yeah.
And what I mean by that is this. We're not just providing a transplantable heart, like a donor heart. Our chief medical officer is a heart transplant surgeon, and he tells the patients that are actually lucky enough to get a heart transplant that we're lucky and we can get you a heart, but really all we're doing is trading one disease for another. And the reason is because the typical heart that's transplanted only lasts about 10 years. And during those 10 years, the patient's life is typically severely compromised. And the reason is, in order to prevent your body from rejecting that donor organ, you have to take a huge amount of immunosuppressant therapy. You have to shut down your immune system so your body doesn't reject that donor organ. It recognizes it as not being part of the body, so it tries to attack it. That's what your immune system normally does. So you have to take a lot of therapy drugs in order to shut down your immune system so you don't reject the organ. And when you do that, you're susceptible to all sorts of things. You could die of a common cold, So you have these major drawbacks of a donor heart. So our solution, our technology addresses all of that. Not only are we providing a heart but we're also doing it in a special way. What we're doing is we're using a patient's own cells, and we're bioengineering, we're bioprinting a replacement heart out of their own cells. We can talk about that process if you like in a little bit.
Yeah, for
But
sure.
but we're providing it out of their own cells. So when we provide this heart to the transplant surgeon and they implant it back or they transplant it into this patient, their body won't reject it because it's made out of their own cells. So they don't need that huge amount of immunosuppressant therapy. So their body isn't subject to all these other diseases. So they have a good quality of life going forward, and they don't have to worry about it only lasting 10 years. It should last them the rest of their natural life. So it's an incredible solution, and there's millions and millions of people whose lives could be saved every year with this technology.
Yeah, I was just thinking, from the sounds of it, it really is dealing with those two main problems, right? But both the lack of hearts that are available and the potential continuous problems that you have after the actual transplant happens.
Exactly.
But I do want to go to the technology itself of Biolife 4D. So you were talking about, and again, it does sound a little bit like sci-fi, printing with somebody's own cells. So is this the bio ink that I was reading about, or is that using the cells that are inside of this, quote unquote bio ink?
So the bio ink actually contains the cells. So let me take a step back and explain our process.
Please. Yeah.
So what we do is a patient who is in need of a heart transplant would go to their doctor, and the doctor would draw their blood. And from their blood, we would separate out their white blood cells. All right, so we have that patient's own white blood cells. Then what we do is, if everyone can think of how the human body is first made, if you will. One cell becomes two, then four, then eight. All of those cells in the embryonic stage, when the baby's first being created, are called embryonic stem cells. Those are stem cells. And the body has stem cells and the body has specialized cells. The stem cells are just like neutral cells that the body can communicate to those and say, hey, we need some blood cells, or we need some hair cells, or some eyeball cells, or whatever. And each of those stem cells has the ability to change itself into whatever type of specialized cell that the body needs. That's the natural biologic process, how every living thing is formed. Every human, that's how your organs, how everything in your body is formed. It's just the natural biologic process. So what we do is we take that specialized white blood cell and we reprogram it to go back to become an adult stem cell. So we reprogram it from a specialized cell back to its neutral cell state, which is that stem cell state.
And sorry to cut you off, but that's a relatively new technology, isn't it? Because in the past, it was only through the embryonic stem cells that you were able to have the stem cells, but now it's actually through the blood cell. So I believe some researcher was able to find a way to actually reverse that process.
That's an excellent point.
Yeah.
So this research using stem cells was really stymied many decades ago, because there are a lot of people that believe that life begins at conception. And by taking these embryonic stem cells and using them for purposes like this, you were potentially killing a human.
Yeah.
And so there was a moratorium against doing this. And about a little over 10 years ago, a scientist from Japan was able to discover that, hey, instead of being unidirectional and cells going from the stem cell state to specialized cells, and then that being it for the rest of that cell's life, I wonder if we can communicate to those cells the way that the body originally did when it was a stem cell, and trick it to go back to becoming a stem cell. And so he actually won the Nobel Prize in Science about a little over 10 years ago for discovering that. So for the first time, we're able to now trick these cells in order to change them to become whatever other type of cells that we want, within a little bit of reason. But for the most part, that's what we can do now. So we're not using any embryonic stem cells. These are actually the patient's own adult, or whatever age they are. It's their own cells. It's their own specialized cells. Okay. So once we've converted their specialized white blood cells back into their own neutral cells, they start to grow just like they do in the body, and they divide and make more and more and more and more and more of them. And we do that, and we work with them up until we have enough volume, until we have enough quantity of cells in order to bioengineer, to bioprint an entire organ. All right. Then what we do is we communicate to those cells again, and we say, all right, thank you for being a blood cell, and thank you for now being a stem cell again. But now we want you to become one of the cells of the heart. So we know what the different cells are that make up the heart. Cardiomyocytes are the type of cells that provide the beating. There's smooth muscle cells. There's about a half a dozen main cells that make up your heart. So what we do is we separate all this patient's stem cells into different groups, and then we change those stem cells into, some of them into cardiomyocytes, and some of them into the smooth muscle cells, and so on, so that we have enough of all of the cells. So we have all the building blocks now for that bioengineered heart. Once we have all those cells, we take those cells and we put them in our bio ink, which is what you were referring to.
Right.
And if you can kind of think of that as if someone had a snow globe and was shaking it, and you see everything kind of floating around, that's similar to what we do with our bio ink. So our cells are in there. We also have nutrients and other things like that that'll help protect the cells during the bioprinting process. And then we have all of this bio ink, which is made up of it's the what we're going to use in the bioprinter. Okay, so now we move over to the bioprinter, and like I said earlier, you can't just melt the cells together. So what we do with our specialized bioprinter is we kind of pick and place the cells. We know what's on each layer. If we were slicing a heart like a loaf of bread, we know what each of those layers are. So we lay the cells down for each of those layers. And then we also put down cells that act like scaffolding if you're building a house. When you're building a house, you have scaffolding to help hold everything in place. until enough of it is built that you don't need the scaffolding as well. Well, we do the same thing when we're bioengineering the heart. We put scaffolding on there in order to hold all of the cells in place. And then we literally print all of the layers of the cells, holding them in place. And then what happens is the natural biologic process takes place. What happens is all of these cells now realize, ooh, we're heart cells. Our job is to join together and network together and start beating and doing all of those things that a heart does. It sounds incredible, but that's just the natural biologic process. And we take that heart, that bioengineered heart, put it in a bioreactor, which is, think of it like a big cookie jar that you drop the heart down into, and instead of submerging it in blood, it's fluids that keep it alive. It provides the oxygen and the nutrients for this bioengineered organ, so it stays viable. Then we take it, pass it off to the transplant surgeon after we've strengthened it mechanically and everything, so it's a fully functional heart. Provide it to the transplant surgeon, and he then is able to transplant it back to the patient. There's also another advantage with our process. If you're a donor heart recipient, whatever heart comes in that's usable for you, that's what you get. It may not be the exact perfect fit. You don't know exactly what shape it is, but part of our process is when the patient's first giving their blood, we also take an MRI scan of their heart, so we know the exact size of their heart. And that way, when we're bioprinting the heart, we can scale that heart to be the correct exact size. So it's not only a perfect genetic match, but it's also a perfect physical match back into the patient's body.
Yeah, that's there's so many things. It's very, very interesting. One of the questions that I have, though, following from that is, I would assume that the entire process can't be done simply by humans deciding which cells go where, right? I do understand that it is a bit of a natural process, and there is some sort of natural way in which the cells kind of figure out themselves. But is there some sort of like automated or some sort of AI being used to lay down these layers of cells?
No, so we're not using AI,
Mm-hmm.
but we do know where the cells all belong. We know that
Okay.
the construct of the heart, we know the valves and where those cells go, and the atriums, all the different components. We know all of that. So we lay the cells down, and it's not going to be exactly where necessarily Mother Nature would do, but that's the incredible thing about Mother Nature. She takes over and she finishes the process for you.
Okay.
At the end of the day, this process sounds so incredible and so unreal, but really all we're doing
Mm-hmm.
is we're recreating the natural biologic process that happens normally with every single human. We're just recreating it outside of the body.
Yeah.
So what we're doing through each of these stages of our bioengineering process is we're literally just tricking the cells to think they're in the body. And and instead of the body signaling them, we're signaling them what we want them to do, and then they just do what they do naturally. We're just kind of recreating millions of years of evolution outside of the body in a short period of time. I wish we could take credit, but the most incredible part of the whole process is really that self-assembly process where the cells know to join together, and then they start beating and everything like that. If we had to figure out that part of the process, we'd be talking about a whole nother game.
Okay.
But we don't. Mother Nature steps in and helps us with that part of the process, and that's really all we're doing, is just recreating that natural biologic process outside of the body.
Okay. Super clear. Maybe the last question that I have on this before we kind of jump into some of the kind of social impacts, which I think are super interesting. You said a relatively short amount of time. What is the timeline of you starting to print to being able to do the transplant itself?
Sure. So the overall process is probably, figure 5 or 6 weeks, but most of that time is the time it takes for us to do the work on the cells.
Mm-hmm.
Because when we take the sample of blood and we take the white blood cells, we then convert them to the adult stem cells, as I mentioned, but we only have a very small volume of them. We don't have a lot of them. So we have to work with those in order to make the large volume that we need in order to print a solid construct like a heart, like an organ. And once we have that volume, then we have to go through that last part of that process, which is changing them into the specialized cells. So all of that work is really the bulk of it.
Okay.
Once we have the BioInk, once we have that and put it into our BioInk, the literally the bioprinting process itself with the 3D bioprinter is only a matter of hours.
Yeah.
And then once that's completed, we're talking only about 3 days that it takes for that natural self-assembly process for the cells. And then another few days for us to continue conditioning that organ before it would be ready to go. So it's about a 6-week process, but most of that time is in that preparation. And it's interesting because most people that have heart disease, some people just, out of the blue can have a heart attack and die. That happens. But most people that have heart conditions know about that.
Yeah.
They know they may have risk factors like diabetes. They may be overweight. They may have had a previous heart attack. Many people that don't die on their first heart attack. They have multiple heart attacks before they die. So people know. So if these people are able to get us their blood cells in advance, what we could do ultimately is be able to take that long part of the process out of it. We can go ahead and take their cells, go through the whole process and get it to that BioInk stage, then just freeze it. And if they ever need it, we're only talking about a short period of time that it's going to take us to finish that off and make that organ available for them for a transplant.
Right. Yeah, that was going to be my follow-up question, but you already answered it. That's great. So I think I want to move into some of the more social impacts. So the very first time that I heard about bioprinting, it of course blew my mind. But the very first thought that I had when I kind of understood what this technology was really that it seemed to be that the black market kind of organ trading industry would be eradicated overnight. Now, I do know that hearts are maybe not necessarily one of the things that are being traded the most. I think it's kidneys and livers to a lesser extent.
Right.
But what are your thoughts on that? Is that really something that could happen if we're able to print out these organs so easily?
Unfortunately, no, in totality, but make a significant dent. So the same thing with donor hearts. It takes time to do the process, and it's an individualized process. So we need to have the cells, we need to be able to create the organ and do that. Some people just don't have that time. Some people may have a massive heart attack, their heart stops, they're on a bypass machine. If they don't get a donor heart right away, then that's it. So in certain circumstance, whenever possible, nobody would ever do that. Most people don't find out that they have kidney or liver failure and say you're going to die though in a week or 2 weeks.
Right,
Sometimes that happens with heart failure, but not typically with kidney or liver failure. So people have time, and even with heart failure, as I mentioned, people typically know. So if we're able to do that, we can bring that period of time down. As another example of that is one of the things we're going to do is unlike kidneys or liver, the heart is made up of different components that are already huge markets. So for instance, heart valves. You've probably heard of people having their heart valves replaced.
Yes.
So there's currently, just in the United States, it's a multi-billion-dollar market for people to have their heart valves replaced. Well, if someone needs to have a heart valve replaced, there's only two options: a mechanical option and a biologic option. And that mechanical option the advantage is it lasts a long time, but there's many disadvantages. One of which is it doesn't grow with you. So if you're growing, you may have to have multiple operations. Another one is because it's mechanical, it tends to throw up clots. You have to go on major blood thinner for the rest of your life to prevent stroking out and dying, right? So that is an option, and it's an off-the-shelf option. But it's not a great option. The other option is the biologic option that's currently available, and it doesn't last very long. They're cow valves or pig valves, but they don't last very long. And so particularly if you're younger, you may have multiple operations that you're looking forward to in your future. And also, again, they don't grow with you. With our valve, if we were able to do a biological valve for that same individual, even if we implanted it as an infant, it should be able to grow with them their whole life, right? And it's a natural biologic valve. So it's a much better option, but there's gonna be people that can't wait for that.
Right.
Anybody that can wait for that will, Anybody that can't wait for that doesn't have a chance, doesn't have a choice. So with back to your question,
Mm-hmm.
it will take, this type of technology will take a big bite out of that for everybody that can wait. Nobody's going to do it through the black market when you have a viable
Right.
option. The reason that black market exists is because there's just so many people who don't have a viable option. And that's the main thing we're trying to address here.
Right. Okay. So we're going to see once this technology is scaled out, we're going to see a massive decrease in the organ trade market industry, but it probably won't be eradicated for at least until some point in the future that we can't pinpoint.
That's very likely.
Okay. Okay. One of the other things that I thought was actually really interesting, maybe even a little bit shocking for me when I was looking at your website, was how you're using the concept of, I believe it's called a mini heart, for reducing animal testing. When I was thinking about human bioprinting of hearts, that was probably the furthest thing from my mind. So if you could touch on that, I think it's very interesting.
It was not something we originally had thought. I should probably lie and tell everyone it was my brilliant idea, but it really wasn't. So what we're doing is we have different milestones on the way to our ultimate goal, which is our full heart viable for transplantation. And one of them is our mini heart. And we look at it as just a proof of concept, at which point it's just a matter of scaling up for a full heart. But as people started to learn about our mini heart, we started to get approached by pharmaceutical companies, drug
Mm-hmm.
discovery companies, and other people. And the reason is this. Currently, any new drug, think about it, new vaccines, right?
Yeah.
Any new
Yeah.
therapies that are going to be released into the United States have to get FDA approval. And in order to get FDA approval, the typical process, you have to do your work in your lab, then you do small animal testing, then you do large animal testing, then you're allowed to go to human trials if all of that is positive. Well, one of the things that they require the FDA requires in this process is testing for cardiotoxicity, which is essentially, is there going to have negative effects on the human heart?
Mm.
And in order to do that, the FDA currently requires them to test on animals. And the reason is because they're a relatively close species, and it's the best predictive model that they have prior to going to humans. The problem is they're a different species, and even though it's the best predictive model that we have, it's not a great predictive model. The number one reason that these new drugs or therapies or vaccines that fail in the market when they get to the human trials is because of negative effects it causes to the human heart. So that's the number one reason. And what that means is that it wasn't picked up in the animal test. The animal test failed to predict that was going to happen. Well, these human trials, inexpensive ones could be $50 million. Expensive ones could be over $500 million. It could be $1 billion. So it's a huge amount of time. It's a huge amount of money that the pharmaceutical companies and drug discovery companies, people working on vaccines, all those type of things are risking huge, huge amounts of money on their new drugs when most of them fail. So not only is the number one reason that something fails because of the heart, the number one reason why something is recalled from the market is because of negative effects to the heart. So there's just not a great predictive model. So what happened was the pharmaceutical companies and other people like that started to hear about what we were doing and heard about our mini heart, and they said, hey, what's a better predictor of what a human heart will do than a human heart, even if it's a scaled down version? So we said, yeah, that's right. And so we started talking to them about providing our mini heart to them in order to have a better predictive model for them before they go and do human trials, which, as I mentioned, is super risky. Most of them fail and super expensive. So if they can have that one last test that gives them the better predictive model before they go out, it's a huge win for the pharmaceutical company. Now, the FDA, their number one charge is safety for humans. Their number two charge, which is below that, is they want to try and reduce animal testing. According to the FDA, they've told us that the number one reason they kick back potential studies to companies is they say, figure out a way to do it with less animal testing, right? So they have a big interest in reducing the amount of animal testing, but their number one concern is safety. So if we can provide them, the FDA, a better predictive model, that means it's safer, which is wonderful for them. And what that would mean is they could then replace the current animal model with our mini heart as the new gold standard. So rather than people having to take the hearts out of living healthy animals in order to test them, right? They'll be able to use our mini heart. So this technology really is the beginning of not just reducing, but working towards eliminating animal testing.
Well, as an animal lover myself, and I think as many of the listeners that I've interacted with have said that they're also animal lovers. I think this is a very positive thing to hear, especially if it's not just the FDA, right? If other parts of the world are also required to have animal testing for these issues that you so eloquently described, we could see a dramatic decrease in animal testing throughout the world in the next several years. Which is
And
awesome.
it's kind of interesting to me because when we do posts or blogs or things like that and talk about we're going to save millions of lives, then there's lots of people that say, great. When we do a post and say we're going to be able to save millions of animals' lives, we get inundated and flooded with, we used to like you, now we love you type
Right.
of responses. So we have a very passionate support group with people that really like animals, or even if you're not a huge animal lover, you understand that it's much better not to be using them for the purposes that unfortunately we really, currently they're needed in order to, promote or to get drugs, therapies, and other things to the market to the benefit of humanity.
Right. Okay. So let's move on a little bit. One of the main themes of the podcast itself is how technologies are impacting jobs. So I think we've touched a little bit on the organ industry. We've touched a little bit on, say, animal welfare. But what do you see your technology really having an impact in kind of what industry? I would assume it would be the medical industry, doctors, nurses, surgeons. Maybe you can touch on that a bit.
Yeah, so that's actually something that we watch very carefully, and the reason is if let's assume that tomorrow we have our full heart viable for transplantation. Well, as I mentioned, there's only 3,500 heart transplants that currently take place in the United States, and only 1,500 globally outside the United States. Well, what that means is there's not a huge amount of heart transplant surgeons, right? We don't, there, nobody needs them. If, like I mentioned, in Israel only does a couple dozen. You don't need 1,000 heart transplant surgeons if there's, only doing a couple dozen of them a year. So one of the things that we have to address, and one of the huge opportunities is all of the different medical support and medical jobs that would be associated with this as this ramps up and gets put out literally on a global basis. So there's going to be a huge need for many, many, many more transplant surgeons, transplant teams, doctors, all of those type of things. There's going to be all of a sudden a very big need and a huge increase in those type of jobs.
Right. Yeah. That makes perfect sense. One of the things that you said, so how I'm also assuming that there hasn't been a full transplant of a bioprinted heart yet, right? The regulations must be absolutely crazy to have that happen, no?
Yeah, ironically, they're a little bit less than, for instance, the valves or other things, and the reason is called compassionate exemption. I'll explain that, but first, no, Biolife 4D, to our knowledge, is the farthest along with this technology of anybody. There has never been a full organ transplanted into a human, other than back in, I think it was 2006, there was a gallbladder that was printed and then implanted into a human. But really, a gallbladder is just kind of like a balloon. It's a sac that holds urine. And so it's not a full 3D construct, solid construct like what we're doing. So it's not really the same thing. But other than that, there's really been no actual organs ever implanted into humans. The other interesting thing is with the different components of the heart that we're doing, like the valves and things like that, it's actually a shorter path to market through the FDA. And the reason is because, as I mentioned before, there's like valve alternatives. There are alternatives. So when the FDA looks and says, here's a potential therapy or medical device, but there are alternatives. So these people have to go through the whole long process because there's currently alternatives. Even though they're not great alternatives, there are alternatives.
Mm-hmm.
With our full heart viable for transplantation, though, there is no alternative. So just in the United States, there's 200,000 people that otherwise whose lives could potentially be saved with a life-saving donor heart. They're just not going to get it. So these are people that have gone to the doctor said, I'm sorry, you're going to die. So there's what's called the compassionate exemption. So we can then go to those people directly. It's a very streamlined FDA process. And we can say, you know what, we believe this is going to work. All of our, everything leads us to believe this is going to work, but it hasn't gone through the whole process. Do you want to try it? Their alternative, they can say yes. And if it works, then thankfully, then they have a good life for the rest of the life. Hopefully, if it doesn't work, it doesn't work. But their option of not doing it is that they're not going to be living much longer anyway. So it's called compassionate exemption. So different things that we're doing have different regulatory paths and take different times. The mini heart, which you asked me about just now, has no regulatory path at the beginning because it's never going to be implanted into a human. Right. So the FDA doesn't have to approve it. All we have to do is show that it's a better predictive model. Then the pharmaceutical companies will use that.
Right. Okay. Super clear. So I think I don't want to take up too much more of your time. One of the last questions that I have for you here is thinking maybe 5-10 years into the future, right? So if we say within 10 years or so, you'll have the opportunity to do kind of full transplants of these bioprinted hearts, but then maybe also go a little bit outside of Biolife 4D. I think that we'll also be seeing, kidneys, livers, most organs of the human being will be able to be bioprinted. Is this something that is feasible within 10 years? And kind of what kind of ramifications will there be for kind of society as a whole and individuals?
Yeah, so the answer is absolutely yes. There are people concentrating on kidneys and people working on livers, and they're making great advancements as well. This technology is highly leveragable, able to be leveraged. So even though it's a completely different organ and completely different cells and they function differently, the same overall process is the same. By taking a patient's cells, by converting them to adult stem cells, in our case, we change them to heart cells. If we were doing a liver or a kidney, it would be those specific cells.
Right.
And I don't want to oversimplify it because it's not a matter of just changing the program and printing a different organ. There's a lot that goes into it, but the overall process is very, very similar and leverageable. Also, the bioinks and things like that are a key component in this whole process. And those can be used for if I could use them for a heart, but I could also use them for a kidney or a liver or something like that. So absolutely, this type of technology is 100% is going to be there. It's going to be there, I believe, well before 10 years. I think it's going to be there within less than 5 years. And
That's awesome.
We're moving very fast, and I know that other companies are moving very fast as well. From a societal impact, it's interesting. We've had over the years, thousands and thousands of kudos and well wishes and all of those type of things. But I did get one email one time from a particular individual who said that they thought I was essentially Satan reincarnated. And the reason is because if God wanted these people to live, he wouldn't have given them heart disease or something else like that. And Earth already has stressed resources and things like that. And if you start saving so many people's lives who otherwise would die, right, you're straining the resources even more. And so that was kind of the thought process that this individual had. And I really sat back and thought about that for a while. And I thought, how do I best answer that? And really what I came up with was that if God didn't want us to have this technology and be able to save lives, he wouldn't have enabled us to do this, right?
Right. Right.
So there are definite social impacts and things like that will eventually need to be addressed. And also this technology, like any other new technology, has the ability to be perverted and used for other purposes other than what we're doing. I'll tell you a quick true story. I got a call from somebody in the Middle East who races camels.
Hmm.
And I guess in the Middle East, camel racing is kind of like we do horse racing. I'm not sure,
Yep.
but he said, I've got my prize camel, and I want you to bioengineer a heart that's twice the size, so we can transplant that into this camel so that it can run much faster, right? And you
Crazy.
can think about that, at some point, if this is a safe procedure, our parents going to say, I want my kid to be the strongest or
Yeah.
the
Yeah.
fastest. And all of those type of things are things that will have to be addressed eventually over time. It'll be a long time we do. But just like any new technology, you have to deal with situations like that and concerns like that.
Yeah, yeah. No, that's actually really interesting. I hadn't thought about the those that line of argumentation, because I think that really fits into like this genetic manipulation technologies like CRISPR and et cetera. Those are
Right.
kind of the typical things, these super babies that we'll be able to create, but maybe we don't even have to go down to that depth to have the same sort of social ramifications.
Sure.
Yeah,
Yeah, absolutely.
yeah,
I mean, the same thing with, IVF and things like that.
yeah,
You're not supposed to, but some people will say, go to a doctor and say, I only want a son, I only want a
yeah,
daughter.
yeah.
And they're very easily able to do that.
Right,
And
right.
it's not how that technology is supposed to be used. But with any new technology,
Mhm.
there's always the opportunity for people to do things that it wasn't its original intended use.
Right. Well, I think that's quite a bit to think about. I think the listeners will really appreciate those kinds of ideas as well. But I do, maybe the final thing to end on. I do think that this technology will be um, more positive than negative, right? As we said, there will be these kind of social ramifications that will lead towards the negative aspect, but from especially the things that you were setting out at the beginning, contextualizing this technology, the amount of people that would be saved from something like this in the future would, my personal opinion, would overstate the kind of negative repercussions that we would have. So, uh,
Yeah, I couldn't agree more. And that's how we came up with the name Biolife 4D, by
yeah,
the way. The 4D, is a play on, we thought maybe 3D because 3D printing, but we chose 4D. And the fourth dimension, according to Einstein, is time.
right.
And really, ultimately, that's our goal, is to give people time. People who otherwise have no hope, give them hope. Right now, if you're 80 years old and they say you're too old to get a heart transplant, well, in my opinion, your life is just as valuable as a 20-year-old or a
Mm,
30-year-old. Just because you're 80 doesn't mean your life is any more valuable. And we want to give all of those people options. We want to give those people the opportunity to continue their life with their families, continue. Young people who, for instance, my wife would probably not be eligible because she has diabetes and a few other conditions. And so if she had a heart situation, she may not even be able to get on the list. Why
mm,
should people like that have no hope? So we're really excited. Everyone who's involved with BioLife 4D is doing it for one reason, and that's because we know the incredible positive impact it can have on humanity, how many lives it can save,
mhm.
and not only save lives, but at the same time give people a better quality of life
Yeah.
going forward. So it's just not saving their life and they're living longer, but it's saving their life and giving them a good quality of life to enjoy themselves and with their families for the rest of their life.
Terrific. Well, Stephen, I think that's probably the best place to end this really interesting conversation. I want to thank you very much for coming onto the podcast. I will post the website details up on the show notes. Is there any other way that you want people to reach out or follow what you and your really interesting company are up to?
Well, as I mentioned, anyone can go to our website, which is
Mhm.
www.biolife4d. That's Biolife, the number 4 letter D.com. And we have lots of really interesting videos and that explain it in a really simple way, the technology, and talks a lot about who we are and what we're doing and why we're doing it. So I encourage everybody to go visit the website. And if anyone ever has any questions, we get them all the time. Trust me. Feel free. There's contact emails and things like that on the website.
Okay.
People are free to ask questions or whatever it is. We love to talk about the technology.
Terrific. Well, thanks again, Stephen. Very much appreciated for you to come onto the podcast. Really interesting discussion. And again, all the best of luck with your company and your work.
Great. Thank you. Appreciate the opportunity. It was fun.
Absolutely. Great. Well, that's it for this week's episode. Thanks for listening. If you like what you hear and you want to support the podcast and the conversations here, the best way to do this is to go onto Apple Podcasts and leave a review, as it helps the algorithm to reach out to new listeners and brings the show to them. Also, feel free to check out the website, automatedpodcast.org, where you can find the show notes for each episode, written articles on the themes of the podcast, and a library of resources on the topic of emerging tech and automation. Also, if you want to reach out and leave any feedback or you have any questions about the podcast or any of the conversations, there are general contact links such as email, LinkedIn, Twitter, etc. for you there on the website. And finally, for those of you that want more than just an audio conversation, the video recordings are now going to be up on YouTube for the newer conversations, so feel free to check out the videos by searching for Automated Podcast on YouTube, where of course you can like and subscribe if you prefer to support the podcast that way.
The Automated Podcast.